Hi, hello. Today we are going to talk about another coding pattern, topological sort. Here I have mentioned few questions. These questions are from Leetcode, so you can practice them. And here I have mentioned the flow. Our flow of study will be the first we will talk about the technical terms, then we will look for what is topological sort, then we will talk about that how we will identify the problem that this belongs to topological ordering. Later we will see what the steps to solve the question, then we will talk about Kahn's algorithm that also generate topological ordering. Finally, we will look for the code template which will be used in most of the question. Let's go with the technical terms. Alright, so these are the terms that we are going to talk about. Let's see what is graph. Hopefully most of you already know about the graph. So graph is actually a data structure or model that represents the relationship between entities. So when we are going to draw that graph, it will be pretty simple. There will be some entity A. It has some relation with another entity B, and B has a relation with C, C has a relation with D, and B has also a relation with D. Now what is node? So node in that graph represent an entity. Entity means that you get some question where we are talking about some person, some student, or might be city, or that could be a subject, or that could be atoms. There could be anything, like any entity we are talking about could be work as a node in the graph. And when we are talking about the relation between them, they can be represented using edge. So let's suppose if I say A is a friend of B and B is also a friend of A, that represents a bidirectional relation. If we say A is a friend of B, but B is not a friend of A, in that case, it is a unidirectional edge. So it means we get about two things. There bidirectional edge and there is a directional edge. Or maybe we can say directionless. It can go here or it can go there in both directions. Now let's talk about cycle. So cycle means that when you travel your journey from a node following the edges, if you get back to the same node, so it means there is some cycle. Let's suppose if you have this node A, it is connected with another node B. This edge is bidirectional. It is directionless. If that edge is being used, so there is a cycle already because we can go from A to B and then we can come back to A again. So there will be the cycle. Let's talk about A has a unidirection, like a directional edge. In that case, we can only go to B. We can't come back. There is no cycle. These graphs are called acyclic graph. But directional graph can also be like cyclic. Let's suppose there is a node A. From node A, we can go to node B, from B to C, and from C to A back there. In that case, we have also a cycle. In that case. Now let's talk about DAG. What is DAG? DAG is a directed acyclic graph. It means we have a direction and there should not be any cycle, no cycle. And we are talking about some graph. So three things. It should be a graph, there shouldn't be any cycle, and that graph should be directed. This is what we call the DAG. Now let's talk about in degree. In degree means that let's suppose there is a node A and there are two edges are coming towards A. So it means that A has two prerequisites. Means you have to complete these two first, then you can come to A to complete it. And what is out degree? Out degree means if there is a node A and there are some edges which are going out. This shows that A says, I am a prerequisite for all of these nodes. So it says, I'm a prerequisite for node B, C, D. Alright, now we can move forward to understand what is topological sort. Alright, now let's see what is topological sort. So topological sort means linear ordering of DAG's vertices such that for every directed edge AB from vertex A to B, A will come before B in the ordering. What does it mean? In a simple word, if I will say there is a graph, let's suppose A to B, B to C, and B to D. This graph should be directed, means all edges should be directed. It should be acyclic, means there shouldn't be any cycle. And that is a graph for sure. So it should be a DAG. In this directed acyclic graph, if someone is going to ask you to write the topological sort of this graph, in that case, the correct topological ordering of this graph will be A must come before B, and B must come before C and D, because A is prerequisite of B, its out degree is 1, and B's in degree is 1. In degree means prerequisite. So first your prerequisite has to be completed, then you can complete B. So this is a valid topological sort. But you can see A, B, D, and C is also a valid topological sort. So there can be multiple topological sorting, which explains that there is a partial sort and there could be a unique ordering. So there could be a unique ordering or partial ordering. What does it mean? It means, let's suppose if I will give you some example 1, 4, 3, and I say you to write its ascending ordering, then there is only one unique ordering, 1, 3, and 4. There is no other solution for that. So this is called unique ordering. But let's suppose if you join some course, and that course have 3 subjects, Algebra 1, Algebra 2, and English. There is one restriction, that Algebra 2 can be done only when you have completed Algebra 1. So what will be the right topological sorting of this graph? You can say, I can do Algebra 1 first, then I can do English, then I can do Algebra 2. It is correct. I can also say English first, Algebra 1, and Algebra 2. It is valid too. If I will say Algebra 1 and Algebra 2, and then I will do English, it is also valid. But we can't do Algebra 2 before Algebra 1. So all these are valid topological sorting. In short, topological sorting pattern is used to find valid ordering of elements which have dependencies or priority over each other. As we have seen in this example, like Algebra 2 has a dependency on Algebra 1. So these are the right ordering of that. So any question where scheduling, grouping, or dependency or prerequisites, such things are coming, where we can use topological sort. Like in real world example, you can see if there is a course, as we have discussed, where multiple subjects you have to do, and some subject have prerequisites. So before doing some subject, you have to complete some subject before that. So there we can use topological sort. Like in Maven also, you can see there we have multiple libraries, and it is also ordering them, making the topological sorting. Like library 1 has to be built before library 2, and then we have to build our application 1, and then also application 2. So also SBT is using the same thing. Also there is a funny example you can think about, like when two friends fight with each other, and after that when they are coming for some solution, that who's trying to blame that whose problem was that, they try to do topological sorting of their arguments. Like they say, you said me this, you said that, then I said you that. and then they are trying to just reorder their discussion. So they are using also topological sorting. Here you can see the number of incidents can happen in some order, like you play football, then you get an injury, and after that you have to clean, then you have to dry, apply medicine, and then you have to bandage dressing. So in real world, on many places we can use topological sorting. The very important thing, whenever you listen some problem, some question, so in that question you have to try to convert the problem to a directed graph. That's the first step. So when you listen the question, you should start thinking, can I convert this problem into a directed acyclic graph where the elements that we are discussing in the question can be presented as nodes, and the relation between them can be represented as edges. And then you can start thinking, oh, I can make the DAG. That okay, if I can convert that, or they're asking for the linear ordering or topological sorting of those elements, then we are for sure use topological sort in those questions. Let's go for the next topic. Alright, so how we will identify that the problem can be solved using topological sort. Might be up to now you have already get the idea that any question which is talking about the partial ordering, where partial ordering is expected, and the ordering is expected on the basis of some dependency or priority among them, then we can use for sure topological sorting. And where we can't use topological sort, even the problem looks like that, oh, there is a graph and dependency or something, but when given problem cannot be converted into DAG, there are some cycles, then, or there is no direction, for sure there is no chance we're going to apply topological sort. And where exactly total ordering is expected, there is a unique ordering they're asking for. Here I have mentioned the summary, like most of the thing that we have discussed before. Now let's see what steps we can do to get the topological sorting. Now let's see how we can solve some question using the topological sort. So topological sort can be solved using two ways. The first we can solve using DFS, depth first approach, and the second with the BFS approach. BFS is, you can also consider it is a Kahn's algorithm. Now in the depth first search, how it works, let's see for the example. Now suppose that's an example of a course where you have to read some subjects in this ordering. In DFS, we are like in general way what you can think about, like if you ask someone, this is my course, how I have to study. So he will say, okay, what is your final subject? So you will say E is my final subject. So he is going to give you the solution, the right ordering of studying these courses in reverse order. Like he said, okay, the final subject you have to study is E. All right, what other subject you have to study before that? You are saying, oh, it has 2 in degree, so C and D. Oh, all right. Now what you have to study before C? You will say B, and before B, A. Oh, what about D? Yeah, before studying D, I have to study C. So this, like on in a reverse order, we are solving the question. Now, for such reverse order, what data structure we can use? We can use a stack. Now, how DFS will work? Let's see. We will take a stack first. Now, how the DFS will work? Okay, we are going to look for this A, and there is a path which is going forward. So we will move forward, and we will see there is a B. Okay, is there any path going forward? Yes, there is C. Move forward. Is there any path? Yeah, there are 2 paths. The first which goes to D and the other which goes to E. We can go to any path. Let's suppose we go to the path E. Now if we go there, after that, once we reach at E, now we are asking the question, is there any out degree? Is there any path which is coming out from E? No, there are no path. So what we will say, oh, that's the final subject we have to study. So put that in the stack. So we will put that in the stack and we will mark that as visited. So we are saying, all right, E, you are visited now. So once some subject or node is visited, we are not going to consider this again. So after that, we will backtrack from here, we will move back, and on our way back, we will ask this node again, is there any further path you can move on? Yes, there is a path which goes to D. Alright, let's go there first. And once we will reach there, we will ask D, is there any out degree we have to move forward? Yes, there is a path which is going to E, but E is already visited, so we can't go there. Now, once we have no out degree for D, you can see there are no arrows coming out. In that case, we can consider, alright, we can put that D in our stack. So we'll put that D in our stack. Now we will move back again. Now we will ask this question C, is there any out degree for you? Yeah, there were two, but they both have been visited. So we said, all right, there is no out degree for you. We can put you in the stack. So we'll mark it as visited and we will put that C in the stack. After that, we will move back from here. And now we will ask for B, is there any out degree? He said, yeah, there was one, but it is already visited and there is no other out degree. So we will say, all right, we will mark you as visited and put you in the stack. Finally, we will get back to our A, and we have already visited its all out degree. We will mark it as visited and can put that in the stack. Now, if we will pop that element from the stack, the ordering we will get will be the correct topological sorting A, B, C, D, E. So this is the correct ordering for the subject we are going to do. That's the way we can solve topological sorting using DFS. Now let's see how we can go with the BFS. So how Kahn's algorithm will work to get us the same topological sort? It is very simple that we are going to use BFS, breadth first search. In simple word, if you're talking to some person, he's going to say you have to complete this course and these are the subject. How you can do, he will advise you pick the subject which you can do right now, which has no dependency. When he's saying which has no dependency, it means he's asking you any subject which has prerequisite or in degree equal to 0. So this is he's asking for. And he said, okay, start working from those subject which has no dependency, and once you done that, look for the subject which have A as their prerequisite and decrement them. So let's suppose if we go for B, once we complete A, we will say, all right, decrement B, and once we will decrement the prerequisites of B, then we will talk about, this subject we can start studying now. Once we can do that, then we can move forward. So this is the way how we are going to apply the Kahn's algorithm. Let's go in more details. So once we are talking about find all those subjects which we can do, so which has the prerequisite 0 or in degree equal to 0, we are going to have a queue. So a queue or list where we will first put all those subjects which have prereq equal to 0. So here we can find that A has no prerequisite, we can put it here, there are no other node, and second will be our answer Q. Now here we can see, so we are saying, all right, I'm going to study A. Yes, I studied that. So once you studied that, you have to look for some operation. You're looking at, okay, decrement 1 from all those subjects who have prerequisites A, decrement their prerequisites. So we can see that B has A as its prerequisites, so it has 1, so we are going to decrement 1, and we found B has no prerequisite now. So once we decrement and we found that any other subject which we can pick and we can start studying, that we will put in our prerequisite next. So we have studied that for sure. A, we can remove it from here. Now we can find, like, okay, this is done. Now we are going to pick B and we will say now B is ready to start studying. So we will pick B, and we will, once we studied that, we will put it here, and we said we have studied B, and we can remove from here. And what next step we have to do? We have to look for all those nodes, all the subject which have B as their prerequisite. We can see C has B as its prerequisite. So we are going to decrement 1 from it. And then we found that, oh, now C has no prerequisite other than B. We have already studied B. So now we can put C as the next subject which we can study. So once we will put it there, after that we will pick C and we will put that in our answer queue. We are saying, okay, we have studied C. Now once we have studied C, again we are going to look for some steps, like how many subjects which have C as their prerequisite. We can see there are 2 subjects, E and D, which have C as their prerequisite. We will decrement 1 from both of them. And here you can see like E has 2 prerequisites, which were actually D and C. So we will decrement 1 from it and we will get 1. And for D, you can see there was only 1 prerequisite, which was C, and we will decrement 1 from that and we will get 0. Oh, now D is ready to study. So we will pick D and put that in the queue. Once we will study, we will put it here and remove it from the queue, and we will say, yeah, it was being studied. Once D is studied, we will do the same operation. We will look for that, is there any subject which have D as their prerequisite? Yes, E. So in that case, we are going to decrement 1 from that, and we will get E 0 here. Now E is ready to study. We will put that in this queue, and finally we will study that. There is no other dependency like out degree for E, and we have completed our course. That's it. So this is how Kahn's algorithm will work. Now for the code template, for sure the steps we were talking about, like here, all these steps you can do in any language. You can pick Java or you can pick Python or any language of your choice, but I'm going to use Scala, and I will be using functional programming to solve these questions. Now we will meet in the next question where I will solve these questions. Like we will identify that these questions can be solved using topological sort, and I will go and solve those questions with the coding template. Meet you in the next video. Bye.